I guess I'll just start with some exam instructions. You know that we have an exam on Wednesday, right? Everybody's looking forward to that? Should be fun. Hopefully it will be fun. You worked hard, so this is the fun time to answer questions. I guess when you don't have a PowerPoint slide, I don't know how to, oh, this does work. Look at that. OK, so we'll start sharp at 12:30 p.m. Please arrive at 12:25 p.m. if you can. Ideally, you should be able to, so that we can all get seated. Have at least one seat between you and any other classmate in any direction. I think we can do that in this room, right? That could be a question also. We're going to use the full 1 hour, 50 minutes. And we're going to be done sharp at 2:20 p.m. because there's a class right after us, as you know, that always waits. It'll be closed book, closed notes. The goal is not to really test your memorization skills. The goal is to test your understanding skills. So hopefully we will not ask anything where you will just memorize and give the answers to. Of course, you should know the fundamentals. But you're allowed to bring a single 8.5 by 11 sheet. And you can write in any font you like. I've seen people write in different fonts. And I don't know why this happened. I always have power problems with my computers, even with new ones, apparently. OK, that's better. And all topics we've covered by, I guess including today, will be on, can be on the exam. And this includes everything. Basically, everything is fair game in the course. So hopefully you know everything. And you've probably seen all the exams. Let's see. This doesn't go fine grain. But you can find sample exams and their solutions on the website. How many of you have looked at it? That's good. Smaller fraction than I expected. I was expecting everyone's hands to go up. You know what?
I will by the test, but I haven't gotten it.
OK. You still have time. That's right. Say it again?
48 hours.
48 hours, that's right. A little bit less than 48 hours, right? 47 hours, 55 minutes. But yes, please look at that, because that will give you a good idea of the style of the exam. And the style will be similar. I guess we could go over the exam. I'll ask you questions. I'll wait for your questions, basically, and Justin will help me in answering some questions, too. I haven't had much sleep in the last few hours. I had a red-eye flight. Say it again? OK. But it should be fun. There are a lot of good, fun questions. Actually, I'll give you an idea of what the questions will be like, since some of you haven't looked at it. Oh, there you go. It's here. And the solutions are there. But what I would suggest, let's see if we can. This new browser, Adobe browser, is not helping me that much. OK, there you go. Wow. Allow full screen. OK, let's allow it. Oh, can you see this one? OK, this is the midterm exam from last year. I guess we had 8 questions. One of them was a bonus. And if you look at this, the first question will likely be similar. So this is basically a potpourri of questions where I'll ask you about, these are simple answers, quick answers usually. And they could be problems. They could be, for example, one example is, which one should be? OK, there you go. In the MIPS ISA, which instruction does not change the program counter? What is the answer to that? No instruction, right? Every instruction changes the program counter in the MIPS ISA. So the answer, if you say none, that'll be a perfect answer. You don't need to write anything else. And I believe the solutions have none as the answer. So it's not easy. Say it again?
What if you jump back to yourself?
But that does change the program. Well, I guess that's a good question. Actually, some people wrote that answer, and I give them full credit. Because that's essentially, that's a way of interpreting the question, right? You can think of changing the program counter as writing into the program counter, or as really modifying the value of the program counter, and they interpret it the way you suggested, and they get full credit that way also. So there could be multiple answers even with a question like this. So write down your assumptions, certainly. Write down what you want to explain. Yes?
Even if you do jump back to the template, you do have the runs delay slot. So you do change the PC and then you back.
I guess that's true. See, you guys are thinking deeply, which is good. So in the pure form of this question, which doesn't have the branch select slot, and which doesn't go into changing the value, the answer is none. But you're absolutely right. Those are correct answers, too. OK? So writing down your assumptions is very important if you're actually thinking differently and deeply. And you will get full credit for that answer that you suggested, for example. But the simplest answer to this question is none. And that will get full credit, too. OK, but you can go over this. Basically, this is a potpourri of questions: pipelining, data dependencies, program counter, endianness, ISA versus microarchitecture. You may expect similar questions: branch prediction, insert into queue instruction, WAX. We covered some of these things, not in detail, but that gives you the idea of a complicated instruction. And the first question will be like this. I can guarantee you that. And later, we have some problem-solving questions. If you have looked at the exam, you will see that there's a question on fine-grained multi-threading. There's a question on branch prediction, basically computing the accuracies of prediction for different branches in a program, since you know how branch predictors behave. It's actually an easy question. So, what does this instruction do? There are reverse engineering questions. These are questions that actually test your understanding. All of these, especially these reverse engineering questions, which I like, are good at testing understanding. And hopefully you'll have fun with this question. I'm not going to give you the answer right now, but I'd like you to take a look at it. And we'll give you the information that's needed for you to answer the question. Out-of-order execution. This is, again, another reverse engineering question where I believe we ask you to figure out, here is the state of the register alias table, as well as the reservation stations in cycle X, or maybe we don't even give you the cycle. Your job is to determine the original sequence of 5 instructions in program order. And we kind of did that in the lecture, right? We looked at the state of the register alias table, as well as the reservation stations, and drew the data flow graph. Essentially, I believe one of the questions here may ask you to draw the data flow graph, but that may be a later exam. OK. And data dependence handling. This is a question on value prediction. This is more of an open-ended question that tests, can you actually think about what it takes to implement value prediction in a real pipeline? So in a sense, this is a more design question. So there will be such questions as well. And this is a more, this turned out actually to be a tough question, but I'll let you figure out how it is. Basically, this is, we gave you this logic last year and asked, what does logic do? It's, again, a reverse engineering question on logic. Once you figure out, it's a lot of fun. And the answer is actually, you can express the answer in 5 words, probably. But I'll not give you the answer. And the bonus question is actually on trade-offs in RISC versus Cisc. You basically write the MIPS assembly code for sophisticated instructions like the enter and leave instructions. These are actually instructions in the x86 ISA, or similar to x86 ISA, which set up the register stack before entering a function call and actually reset the registers before leaving the function call. You can have single instruction doing each of those functions. And this bonus question tests how you can write that code in MIPS ISA. So it's actually an easy bonus question. So one other thing I would suggest when you get the exam is take a look at the questions and try to figure out what you would like to answer first. You don't have to go in order, right? You can schedule your time, just like instruction scheduling. OK? And we give you the instructions that you need. You don't really need to memorize any of the instructions, although you should be familiar with these instructions from your labs, right? We're not necessarily going to give you every single information related to the instruction, but this is more of a summary sheet. And you'll have scratchpad pages. OK, so this is just to give you an example of what the exam looks like if you haven't looked at it yet. Let's see if there's any other information that I would like to cover. And you know that there were extra office hours. And this is the review session. And you have my tips, hopefully. I guess I'll, yes?
I was going to say, I was looking through some of the other old exams, and there were a bunch of like page table and caching problems, which we covered in class, sort of, but not to the extent that you might make a problem out of it. I mean, should we expect anything like that?
So that's a good question. I think you're referring to questions that look at the interaction between address translation and caches, right? Data caches, L1 caches. There won't be any question like that because we haven't covered caches yet. We'll look at that, the interaction between virtual memory and caches at that time. But I will expect you to know what are the basics of virtual memory, how is translation done, how is translation accelerated using the translation look-aside buffer. What do you need for protection? What is segmentation versus paging? But you won't be expected to know the interaction between virtual memory and paging. Virtual memory and caches, OK? It's a fun topic, though. Maybe you will be expected to know it later on in the course. And it's actually a lot of fun to understand how those interact. Yes?
How many different kinds of branch predictors would we be expected to know the internals of? So there's the global history, and then there's the local history. It's the same thing, but per instruction.
Per branch, yes.
And then there's the tournament that combines the two.
That's right.
I think I'm missing a few.
So I guess I can go over that. That will be the first question, huh? Well, whatever we have in the lecture notes, I think you need to know the concepts, right? Global history predictors operate based on the concept that branches, different branches, are correlated, right? And one way to think about these are actually having, these are two-level predictors, right? They use two levels of history. One level is the global history register, which direction the previous n branches went, if this is n bits. And you use that information, that context information, to index into the pattern history tables, which basically tell you what direction the branch that you're trying to predict went when you saw this history last time, right? So this is the global history predictor. And you should know why this operates, for example. And hopefully, since you were all in the lecture, you know why that works, right? And the answer is because there's correlation between different branches. So basically, this question that I showed you earlier tests whether you can step through how this works. So this is one predictor. The other predictor is local history-based predictor, what you suggested, which is you take the program counter, and each branch has its own local history. Basically, at the first level, you have a local history for the branch. The last n times, if this local history is n wide or m bits, which direction this particular branch at this particular program counter went the last n times it was executed. And you take that, index into a pattern history table to see which direction this particular branch went when you saw this history last time for that branch. Right. So we covered this in class, and this operates. This works because of a different reason, right? Because the same branch itself is correlated with its past instances. And you can go into the lecture notes to figure out code examples. So these basically work because of different reasons. That's why people have developed tournament or hybrid predictors. I'll call this hybrid predictor. Tournament predictor is actually the name that was given to the alpha 21-264 predictor, right? One example of this, of which is the alpha 21-264 predictor, It's an example, let's say. Tournament predictor. And the idea is some branches are predictable, or sometimes the branches some branches are predictable using this predictor. Some branches are predictable using this predictor. So why not combine both? You have the, I guess I'll call this the global history predictor, and the pattern history table for that. And you have the local history predictor, registers. And with the program counter, you do this. And you get a prediction here. And you get another prediction here. And the idea is to select between those. Okay. Then the question is, how do you select between those? Basically, you need a meta predictor or selection predictor that chooses which predictor was doing well. And this could be based on different information. And I believe, if I remember correctly, and you don't necessarily need to remember this perfectly, since I do not remember, I can look it up, right? I believe in Alpha 2164, this predictor operated based on the global history register. Basically, this meta predictor, the last time I saw this history, the local predictor was correct or the global predictor was correct. That's what this meta predictor keeps track of. Make sense? You could do it in different ways, but the designers of this machine found out that this was a better identifier of which predictor was doing well. For example, you could do it based on the program counter, right? Maybe based on the program counter of the branch, you can distinguish which predictor is doing well. That separates branches into easier to predict with this predictor versus easier to predict with this predictor. But designers of this machine, I believe, use the global history register to decide which predictor was doing well. Make sense? Okay, so basically you need a selection mechanism. So I think I'm going ahead of your question, explaining these different predictors. So these are three predictors that you should have a very good idea of. But there are other predictors, of course, right? We've looked at other mechanisms, different static prediction mechanisms. And what are those? Always taken, always not taken, right? Or backwards taken, forward not taken. Right? That's another predictor. We've looked at profile-based predictors. I'm not going to go into detail on a lot of these, but I'll list them. We've looked at program analysis-based predictors. And these were the predictors that actually, where the compiler figured out the likely direction based on the analysis of the program. So for example, if a branch condition is based on comparing a number, a floating point number, to another number, then the compiler says, it's unlikely that this floating point number will be equal to this other number, so I'm going to predict this branch, or insert a hint bit to this branch saying that it should be predicted as not taken. Make sense? And we've seen different examples. For example, error codes. People have found out that branches that are testing errors are usually not taken because programs usually don't lead to errors, right? So you can, the compiler can figure out based on analysis that this branch is actually testing whether or not there's an error in the program. If that's the case, it can insert a bit saying that predict this branch as not taken or not going into the error code. Right? Similarly, exception-causing branches, right? Branches that test for exceptions, they're usually predicted not taken because if there's an exceptional condition, the program will end anyway. Okay? So program analysis-based and the programmer-based predictor. Programmer can actually insert static predictions, right, using pragmas. So these are all topics that we can ask about. What's a pragma, for example? That could be a good exam question. Although we won't probably ask it that way exactly, what's a pragma. But we may give you examples of something and ask you what that is an example of. You know what pragmas are, right? Yes?
To the compiler.
Say it again?
Hints to the compiler in the code.
So that's, yes, that's one way of looking at it, but it's more of a programming language construct. So it's essentially a construct in the programming language which enable hints to the compiler, right? Which enable actually hints to the compiler to do something with the code, which the programmer inserts. Okay? So it's something that can be manipulated by the programmer. Did I forget anything? Any other predictor? Static predictor? So that's now dynamic predictor, right? Yeah, so we can take a look at that. Dynamic predictors. We start out with the simple ones, right? Last time predictor. This basically predicts the direction of the branch as the direction it took the last time it was executed. This is the simplest one. It's dynamic because it's using information from the execution of this particular program itself, not based on some static information that's available without executing the program.
So it's basically a local history predictor with a 1-bit a local history register.
This one?
Yes.
No, so it's not a local history predictor actually, because with the last time predictor, you don't have this local history. You can think of the last time predictor as you eliminate this one, and you straight go into the prediction. It has 1 bit, right? Yeah. So it's not 2-level. This is still 1 level of history. Okay. Make sense? Because you're not looking at the history in this branch to index into something else. So, and then we had the 2-bit counter-based prediction, right? Which was also called the bimodal predictor. And the idea here was this last time predictor changed its mind very quickly, right? If a branch went to another direction once, the last time predictor changed its mind, right? And this was bad for loop branches. When you exit the loop, the branch is not taken. So you mispredicted at that time. But when you re-enter the same loop, when you come to it, assuming that the loops iterate many times, you will mispredict that branch again. Because the last time the branch was not taken when you exit that loop, because it's the same loop branch. So you would mispredict that loop branch twice out of n iterations. And if n is small, your misprediction rate for that branch would be high. So the idea here is to add some hysteresis, such that the predictor doesn't change its mind so quickly, change its prediction quickly. So basically, the idea is if you have a 2-bit counter, it takes two different outcomes to change the prediction, instead of only one different outcome to change the prediction. Make sense? The branch needs to go to be, let's say, taken twice in a row to be predicted taken, instead of whereas here it needs to be taken only once to be predicted taken, right? So that's the idea. Again, this uses only a single level of history, right? You don't have this level. You have program counter directly indexing a pattern history table, and you have 2 bits here now. And you remember the 2-bit state machine, hopefully. Taken, not taken. So you have 4 states. Weakly taken, taken, weakly not taken, and not taken state. And you probably know the transitions here, right? I'll not draw that state diagram. OK? So this is the 2-bit counter-based predictor. And then we figured out that this is not enough because the accuracy of this is not high enough, because it's not exploiting correlation. And then we talked about this global history predictor, and then local history-based predictor, which I described, and then the hybrid predictors, which actually can combine many different kinds of predictors. So hybrid predictors are actually more general than just this, local plus global. This is one example of a hybrid predictor, right? You could actually have, let's do this. You have the program counter and index into whatever I showed you, a pattern history table directly, let's say. And this is a bimodal predictor, right? So you could have 3 predictors, and this could give out a prediction. And you could be selecting from these 3 different predictors. And many processors today actually have more than 3 predictors. OK. So that's the hybrid predictor. And we also looked at a special case of a global history predictor, a little bit more sophisticated than the global history predictor, which we call the G-share predictor. Do you guys remember what this is? No? Guess you haven't looked at the branch prediction lectures yet. So the idea here is, oh, where's my global history register? There you go. That was the global predictor, right? You have a global history register and pattern history table. You have the global history register, which direction the last n branches went. And normally, a global predictor, you use that pattern history to index into the pattern history table, which gives you, let's say, 2-bit counters that tell you last time you saw this history, which direction the branch went. Weekly taken, weekly not taken, or not taken. One problem with this is this history doesn't really distinguish between different branches, right? Maybe some branch is taken when you see the same history, but some other branch is not taken, right? So you have aliasing between different branches. So the idea in G-share predictor is to reduce that aliasing a little bit. And how is it done? It's done in a simple way. Basically, you take the program counter and XOR it with the global history register value and use that as the index to the pattern history table. So what does this buy you? It gives you more context information about the branch you're currently predicting, right? Not only the history, but also which branch are you predicting. And it turns out this has much higher accuracy than just using the global history register alone to index, to build your global branch predictor. I think this was one of the predictors you were looking for, right? So why does it work? Basically, it gives you more context. The other reason why it works is actually it distributes the entries in the pattern history table. So if you have an XORing mechanism, basically you're hashing one number with the other number, you get better utilization of this pattern history table. Whereas if you can use more bits. So for example, if your global history register was always 1, 1, 1, 1, 1, 1, 1, 1, 1, you would always be using only one entry here, right? Whereas by distinguishing between different branches, you would be using more entries. So it gives you this randomization effect, which we will see in caches later on also. People use this kind of randomization methods to better utilize hardware structures. OK? Let's see. I think that's all. We didn't cover beyond this. But you should take a look at the lecture notes, obviously, the branch prediction lecture notes. OK. What else? I would actually encourage you to go and solve the exam yourself, first midterm, and actually look at the final exam as well, because final exam from last year also has concepts that we've so far covered. Maybe not so much midterm 2 from last year, because midterm 2 was more focused on the second half of the course. But do solve the problems yourself, test yourself. And we do have the solutions online. All of the solutions are online, and they're detailed, so they should give you information. They should help you out a lot, hopefully. That way you can gauge yourself. What else? I'm happy to take more questions here. Yes?
How we decide whether features can be outside of microarchitecture?
Oh, how we decide what's part of the ISO or microarchitecture. OK. Should we try to solve that exam question as a way of answering your question? Let's see how I will do on the exam without much sleep. So there was an exam question, that one, from last year. And I'll use this as a case study to answer your question. Basically, we ask you indicate whether each of the following design choices in a processor is a feature of the ISA or of the microarchitecture. I guess what is the difference between ISA and microarchitecture? ISA is essentially what the programmer needs to know, right? ISA is the interface between the software and the hardware, which includes everything that the programmer needs to know, or some programmer at some point in time needs to know to write programs for that particular machine with that ISA, okay? So if it's visible to the software at some point, then that's part of the ISA. If it's not visible to any programmer at all, then it's not part of the ISA. So that's the key distinction. So that's the litmus test we're going to apply. Two-level global branch prediction, how appropriate. We just looked at it, right? This is the two-level global branch predictor. Level 1, global history register. Level 2, pattern history table. Is this visible to the programmer? Not at all, right? So the answer here is this is part of the microarchitecture because it's not part of the ISA. On the other hand, if somehow you had an instruction that did this, this could be in a question, right? Let's say I define an instruction that gives the programmer the ability to set the bits in a pattern history table. How so? Let's say you have an instruction that says set GHR. I'll somehow figure out where these things are by the end of the semester. Let's say I cook up an instruction that says set GHR and maybe R1 to the value 0. And I'll define the semantics of this instruction as, well, you don't even need to know what the semantics of the instruction are, right? Just because this instruction operates on the global history register, now this two-level branch predictor is visible to the programmer, right? Because the programmer can set something in the global history register or using the global history register to some value. Make sense? Now we made it visible to the programmer. That'll be part of the ISA. Okay? I won't go any further, but what I was going to suggest is the semantics of this instruction would be pattern history table at R1. I don't know what I did here over here, but equals, I'll call this immediate. And immediate can be 0 or 1. I guess then you don't need the GHR, right? Now the pattern history table is visible to, let's do this, set pattern history table entry that's pointed to by R1 to this immediate value. Make sense? Now why could this be useful? This could be useful if your pattern history table entries are actually set by the compiler. Right? If the compiler somehow figures out that at this history, most of the branches are taken or not taken, the compiler may want to use this instruction to set the pattern history table entries, right? If you have this ability. So there could be use for something like this. And that could be a nice question also, actually. I don't think we'll have it in the exam, but we could give you this instruction and give you the semantics of it and ask you why could this be useful. Right. It could be useful if the compiler has knowledge about a particular pattern, global history register value and where the branches go with that global history register value, such that in hard code, the prediction for that given global history register value. Make sense? OK, let's take a look at this one. Predicated instruction execution. Is that part of the ISA or the microarchitecture? ISA. So everybody agrees that that's the ISA, I think. And that's kind of obvious, right? Because there are instructions that set the predicates, for example, which means that it's visible to the programmer. And there are instructions, predicate bits are part of the instructions. In the ARM ISA, for example, the condition bits are part of the instruction. OK, a floating point unit that uses white floating point values for additional accuracy. Is this part of the ISA or microarchitecture? This could be tough, huh? No? Who says ISA? Okay. Who says microarchitecture? I guess it really depends whether you expose this to the programmer or not, right? But most of the time, this is actually exposed to the programmer. Otherwise, how are you going to take advantage of this, right? So this may be a place where you explain what your reasoning is for the microarchitecture. I would say this is part of the ISA, because the floating point unit, the purpose of it is whether you have a 64-bit wide floating point unit or 128-bit wide floating point unit should be exposed to the programmer for the programmer to take advantage of it. Although one could argue also that you could have some additional accuracy in your floating point unit itself and not expose it to the programmer, but give you a more accurate answer given the number of bits that are already exposed to the programmer. So I think here the answer can go both ways. Make sense? So sometimes not everything is very, very clear. But I'd expect you to give a brief reasoning of why you think that way. You don't need to give it for all of these, but for things that you believe could be ISA or microarchitecture both, just give your reasoning, and you'll get full credit. OK, a 32-bit wide data bus to memory. What do you think? ISA or microarchitecture?
Well, the word size is going to be part of the ISA, but you could have a different word size than the size of the bus in memory.
Absolutely, yes.
Stupid.
So this is part of the microarchitecture, right? Because there's no reason to expose, there may be reasons to expose this, but it is not exposed today to the programmer. OK, an additional set of user visible registers. This may be the freebie in this question. ISA, right? Yes. It gives you even user visible here, so if it's visible to the user, then it must be part of the ISA. OK? Does that answer your question? OK. What else? I can see you guys are solving the next question while I'm waiting for a question from you. Yes?
What about conditional codes? Are they part of the ISA?
Oh, condition codes.
Can they be part of just the microarchitecture and not ISA?
That's a good question. Can they be part of microarchitecture and not ISA? Well, I suppose the condition code name itself refers to something specific, which is actually part of the ISA, right? Basically, you have these codes that are set by instructions. And if it's set by instructions, then by definition, it should be visible to the user. It's in that document, right, that says condition codes are set by instructions. But you could think of things like condition codes that set conditions but never get exposed to the user. Then we wouldn't call them condition codes, though. Okay. So condition codes are part of the ISA. Another way of thinking about it is it in this document, the ISA document? Although there are a lot of things sometimes in those ISA documents that specify microarchitectural things too, so you've got to be a little bit careful. What else? We've covered a lot of topics. We might have some questions on some other things too. Yes?
Did you ever calculate branch misprediction penalties?
Say it again?
Branch misprediction penalties?
Calculating branch misprediction penalties.
Yeah.
Okay. Okay, that's a good one. I don't know if we have any question over here. Is your question inspired by an exam or?
Not particularly.
Not really? Okay. So what is the branch misprediction penalty? Basically, the branch misprediction penalty is I guess you could define it in different ways, but one way of defining it, and the way we've defined it in the lecture, is how many instruction slots have you actually lost because you mispredicted this branch? Right? This could be specified in terms of cycles or instructions. The way I described it just now is how many instructions slots have you lost? Meaning, how many instructions could you have processed more if you hadn't mispredicted this branch? This could also be defined in terms of cycles, in which case the answer is how many cycles does it take to resolve this branch and redirect fetch to the correct path. Does that make sense? And instructions is basically cycles times cycles per instructions per cycle you can do. Right? Basically, number of cycles to resolve a branch and redirect fetch to the correct target. And if you talk about number of instructions you wasted because of the branch misprediction penalty, it's essentially the number of instructions you could have executed in these number of cycles. Okay? Do you want to go deeper? There's one question that we had in class. Maybe you're thinking of that.
There might have been something on the. There may have been one on one of the older exams.
Older exams. That could be true.
Yeah.
But you can take a look at it.
Okay.
But that's the definition. So for example, actually, let me give you, just to go over the lecture notes, that. I'll find where it is, but I believe this is it. PDF will be easier. Yes, this one. Okay. Here, for example, if you remember, I guess I should do this. Okay. We assumed a 5-wide superscalar pipeline with 20-cycle branch resolution latency. And we didn't talk about how long it takes to redirect the fetch. But the assumption here is if you have a 5-wide superscalar pipeline and it takes 20 cycles to resolve the branches, the branch misprediction penalty is 20 cycles. Now, if you have an out-of-order machine, it could take longer, right? Because the branch may be waiting for a data dependency. But this is a minimum branch misprediction penalty, 20 cycles. And basically, in terms of instructions, while you're waiting for the branch to resolve, you could have fetched 100 instructions, right? 20 times 5. That's the branch misprediction penalty, minimum branch misprediction penalty for this machine. Right? And I mean, this is a perfectly valid exam question also, actually. And I'm hoping this is easy for you now. We had the question, how long does it take to fetch 500 instructions in this machine? Assume that there are no fetch breaks, which means that you always fetch 5 instructions per cycle. A fetch break is when you have to break the fetch of a wide fetch engine because maybe there's a jump to somewhere else, some other cache line. But we're assuming that there are no breaks. And 1 out of 5 instructions is a branch. If you have 100% accuracy, you fetch 500 instructions in 100 cycles because you're fetching 5 instructions per cycle. Right? If you have 99% accuracy, which means that 1 out of your 100 branches is mispredicted, what are the number of cycles you need to fetch? So how do you calculate this? We're fetching 500 instructions. 1 out of 5 instructions is a branch, which means that 100 instructions are branches. And 1 out of those 100 is mispredicted, which means that once within these 500 instructions, you go on the wrong path. And when you go on the wrong path, you spend 20 cycles, which means that it takes that 20 cycles on the wrong path, plus you need to fetch all of the instructions still to be able to finish them, plus the 100 cycles that you need to spend to fetch those 500 instructions. So you need to have 120 cycles to fetch those instructions. Right? Which means that you need to fetch 20% extra instructions. So that's how you do the calculation. Make sense? And I believe, let me go quickly to relate it to your question. Here, typical branch penalty. This is actually the alpha 21264 tournament predictor, the hybrid branch predictor that was used in alpha 21264. They say the minimum branch penalty is 7 cycles. This is the branch misprediction penalty. It takes, at a minimum, 7 cycles to resolve the branch, from fetch of the branch to execution and redirection of the pipeline. But they also say typical branch penalty is 11 plus cycles. I took this actually from the alpha 21264 microprocessor paper. Why is that typical higher than the minimum? Well, because they had an out-of-order execution engine, which means that you don't get to execute the branch after 7 cycles all the time, because the branch could be dependent on a load instruction or some other instruction. And after the branch is fetched, it takes about 11 cycles for the data values of the branch to be ready to execute. So your branch misprediction penalty can actually vary. Make sense? Okay. Okay, I won't go into more detail. You guys like branch prediction today? We covered other things in the course too. But do solve the branch prediction question on the test. It's fun and it's relatively easy once you understand the concepts. We just need to be careful with the boundary conditions, because sometimes initially the branch can be mispredicted, right, depending on what your pattern history table values are set to. And your loop exits and entries, you need to be careful with those, because those are the times when you actually mispredict the branch with different predictors. Any other questions? Everybody's ready, I assume? Yes, there's one hand.
So for the past exams, like it seems like the people did really badly on the test. What did they seem to miss most often?
Oh, that's the toughest question probably. For the past exam, that's a good question. Maybe I'll try to remember. So I'll try to answer everything. Let's see. Looks like me, huh? Where did we have this?
I think in their homepage it was the link to the last year's course.
Oh, that's right. Yes. Oh, okay. There was something. I believe we did give out the per question breakdowns.
Oh, it did. Okay.
I'm not sure if it's on the exam. Justin may know this better. Midterm 1 grades distribution. But you guys will do better. Yeah, I believe one of the lectures had the per question breakdowns, and I do not remember actually which lecture had that. Maybe if we dig it up later today, you may want to go back and backtrack when the midterm was and when the exams were distributed. You can probably figure that out. But if I remember correctly, if we go back to this midterm that was there, and I'm hoping this won't be the case this year. You guys will all do all of the questions well. So there are certainly questions that can be missed here. But if you know the concepts, this question should go relatively well. I believe a lot of people missed this particular one. I remember this one, register dependencies. Yeah. Okay. Let me actually solve this question for you. This is This is a really easy question, and I repeated this answer many times in class. What is the fundamental cause of false register dependencies? What is a false register dependency? Output and anti, or write after read, write after write dependencies. What is the fundamental cause? Why are these dependencies there in a program? Yes? Absolutely. That's the answer. 3 words. We don't need anything more. Not enough registers. If you can do it in 2 words, that's also fine. So that's the answer, basically. And I think some people missed that. Maybe they took the question wrong, but we're not trying to trick you or anything. That's the answer. What can be changed in the ISA, compiler, and microarchitecture to eliminate false dependencies, if at all possible, in each of the 3 levels above? Describe one disadvantage of each approach. This is a tougher question because it requires you to think a little bit, right? What can you change in the ISA? More registers, right? Again, 2 words. What is disadvantage?
More expensive.
It's more expensive, yes. I mean, here you can actually write a lot of reasons, right? Your instructions become larger, for example. That could be code size increases. That could be true. What about compiling?
Reordering.
Yeah, reordering can eliminate some of these dependencies, at least in the sense that these dependencies will not be exposed within the pipeline, right? If you find independent instructions and separate the dependent instructions far enough apart, maybe the dependencies will not be fully eliminated. They'll still be there, but they won't be exposed. So that answer I will accept, reordering. Or you could do much more aggressive register allocation, right? That's another answer. Much better register allocator at the compiler level, such that you don't need as many registers. That eliminates dependencies. Okay, microarchitecture. How do you eliminate those dependencies?
Data forwarding.
Say it again.
Data forwarding.
Data what?
Data forwarding.
Data forwarding. Then you don't eliminate dependencies, right? You still have the dependence, but you supply the value quicker. Yes?
Renaming.
Renaming, absolutely. You rename at the microarchitecture level. At the architecture level, you have fewer registers, which lead to these anti and output dependencies, but you rename them to a larger register file or reservation stations, such that they're not a problem anymore, because you have microarchitecturally a much larger number of registers. So you guys have answered the question perfectly now. That's it. But this was actually one of the, I believe, one of the harder questions. Okay, let's see what else. Branch prediction. Actually, I don't remember. Maybe my memory would be better if I had slept better. This may have been hard. This was a harder question. What does this logic do? This was a hard question because it's required to think a little bit out of the box. It's not that hard, but it's a little bit hard because we don't exactly give you what these mean, and we don't exactly give you what these necessarily mean, but you can figure out, right? You guys are all engineers. Op1 source, op1 source 2, op2 source 1, op2 source 2, op3 source 1, op3 source 2, and they come from the register alias table. Now you need to know what the register alias table is. And there are architectural register numbers that come from op1 destination, op2 source, and you can follow these things. And there are some priority encoders that give you some priority that control these muxes. And the outputs, at least we give you the inputs and the outputs. Outputs are op1's source 1 tag, op1's source 2 tag. You have 2 sources. And op1's destination tag. And destination tags are always connected to the destination tags that are inputs, if you look carefully. Basically, you get the source tags and the destination tags for op1, op2, op3. Any guesses as to what this could be? Or maybe I'll let you figure out individually what this is. So this was a tough question in the exam because we never actually showed this in lecture. This is the logic that does this. And I believe you can answer this with 3 words, right? Yes. Are you going to give the answer?
Doing checking whether you're like where it should take the data from. Like if you need data from a alias table or the last architectural state.
Not exactly. But it's determining something like that, but not exactly what you said. But I'll let you figure this out. I don't want to spoil this for everyone. Yes?
I was going to ask, would a question like this be all or nothing? Or whatever, a description that's sort of correct, that has some right aspects, gets some credit?
So we do give partial credit. So you will get partial credit if you actually explain your reasoning, assuming that your reasoning is in the correct trajectory, of course, right? If it's totally incorrect, then you won't get partial credit. But all or nothing actually was the intent with this question, but there were some answers that generated partial credit. Okay? So this was actually an easy question. So the bonus was an easy question. Don't think that because it's bonus, it's going to be hard. Bonus is just bonus, right? It doesn't say easy or hard. And hopefully, if you know something, that's easy. Right? So you should take a look at what the question is. Okay, I think that answers your question, right? What else? Let me see, maybe we can solve one more question here, just to warm you up. Let's solve one of these. Yeah?
We're not expecting to know any of the details of, for example, the MIPS. The MIPS is particular implementation of virtual memory. Right?
No, we won't ask you that.
Okay.
Yeah. If we ask you something like that, we'll give you the background. MIPS does it this way. Why so, for example? That could be a question. Because that way we'll expect you to give us the trade-offs of why MIPS does it this way. But you don't have to know exactly why MIPS does something. Okay? Exactly how MIPS does something. So we don't want you to memorize things. We want you to be able to make the trade-offs based on the understanding of the fundamental concepts. Okay? We can give you, for example, MIPS implements software-managed TLBs, right? Translation look-aside buffers. And we can ask you, what is the advantage of this? What is the disadvantage of this? And that could actually turn into some problem question where you actually calculate how long it takes to handle the translation look-aside buffer misses. Okay. Okay, here, another. Let's see. What should I solve? Okay, actually this could have been thought of as a hardware question, but a lot of people got this right. You can see this more of a puzzle, but this question actually tests understanding a lot too. In a blank processor, the hardware detects the data dependencies between concurrently fetched instructions. And if you look at concurrently fetched, that's in italics. That should give you a hint. Actually, you don't really need the rest to answer this part. What is that blank? Superscaling, right? In a superscalar processor, the hardware detects the data dependencies between concurrently fetched instructions. You're fetching multiple instructions in the same cycle, and the hardware needs to detect the dependencies between them. In contrast, now we're going to contrast with something that doesn't do this, apparently. Now this is going to be a little bit harder because we have two blanks. In a blank processor, blank does. What would you normally contrast superscalar with? You know this from lectures, right? Not superscalar. Not superscalar. Architecturally, you know. Yes?
VLIW.
VLIW, right? Because what does superscalar mean? Superscalar means multiple instructions fetched. Multiple instructions are fetched, decoded, executed concurrently. There are two paradigms that do this. One is superscalar, and the other is VLIW, that we covered in course. So in a VLIW processor, well, in a superscalar processor, the hardware detects the data dependencies. In a VLIW processor, software. Software is enough. You can say the compiler, that's also fine. But to preserve parallelism between the sentences, it's really software, right? But compile is also okay. Okay? Yes?
So no, if we got like all of the blank except for like that one, would we lose all of the credit or would we get like partial credit?
You'll get partial credit, don't worry. Depends on how reasonable the answer is though.
Right.
But we will give you partial credit. So. But don't be verbose just to get partial credit. Okay, let's see what else is here. Do you want to do one more question? Yes? If anyone has some other questions, we can certainly do that also. But somehow I'm not able to figure out how this PowerPoint seems to work. Need better software, right? Yeah, we did the ISA versus Microarchitecture. This branch prediction question is easy, so I'll let you do that. But maybe let's take a look at this one. I guess this is closest to the memorization we will get, but this is such a fundamental concept that you should really know what this is. So this question says the VAX has an instruction inSQ. Oh, I see what I did. That's fine. Oh. Okay. inSQ pointer 1, comma pointer 2, which causes the node pointed to by pointer 1 to be inserted into a doubly linked list immediately after the node pointed to by pointer 2. We say the doubly linked list is a blank in the VAX ISA. What is doubly linked list in the VAX ISA? If there are instructions that operate on doubly linked list. Data type, right. That's it. So you guys will do well. Okay, what else? I'll take more questions. That was my original intent. I'll take your questions. I won't volunteer any questions, right? Yes?
What is the weightage of this exam in that course?
Oh, what did he say? 15%? I believe it's 15% of the entire course, right? But you'll have to check the syllabus. I don't remember. I guess we could do that. Since I'm going to answer your questions. Let's see. This one. There's the syllabus. Yeah, there you go. It's 15%. And midterm 2 is 15%, and final is 25%. What else? Or should we take a break? Or do you want Justin to go over some exam questions? I'll do whatever you tell me. That's the purpose of this session. Shall we do more questions? Exam questions? Yes? How many people want that? Not everybody wants it. Well, we could. Who has a question? Burning question that's separate from the exam question. I'd like to take those first. No? No one? Okay, maybe we can do some more exam questions. Justin, you may want to do one of the questions, but let me do one more. Let's see. I think I'll do a question from the final last year. Oh, there you go. Beautiful. First question. Please explain the following concepts, each in no more than 20 words. Superscalar processing, out-of-order execution. What is superscalar processing? Yes?
Is the difference between these just the superscalar always issues in order, whereas the out of order issues in whatever order it feels is best? And they still have to be reordered at the other end?
No. So, no.
No?
These concepts are totally orthogonal, actually. Superscalar specifies nothing about in order versus out of order. And out of order execution specifies nothing about multiple instruction fetch versus single instruction fetch. Many times these concepts are coupled, and people do confuse these. That's the purpose of this question, actually. They're orthogonal concepts. Superscalar means multiple instruction fetch, decode, execute purely in hardware. Right? If you write that, that's a good enough answer. Out of order execution means instructions are dispatched into the functional units out of the original program order. That's it. There's not even a specification of whether or not they're reordered at the end, right? Out of order execution is basically you execute instructions or dispatch instructions into the function unit out of the program order. And if you think about this, out of order says nothing about whether you're fetching 1 instruction or 10 instructions per cycle. Right? Could be both. Well, it could be either. And superscalar says nothing about whether you're executing instructions in program order or out of program order. Make sense? So there have been superscalar processors that are out of order, for example, Intel Pentium Pro, or most of the processors that you're using today, Intel processors, AMD processors. And there have been superscalar processors that are in order. Which ones? Intel Pentium, for example, is an in-order processor, Pentium 2. 2 wide in order. They didn't do out-of-order dispatch into the functional units. Alpha 21164 is another example. 4 wide in-order machine. Superscalar, but not out of order. Alpha 21264, superscalar and out of order. Okay? So I've given you the answer, I think. Oh, yeah, there you go. There's more to this question. Okay. Are the concepts of superscalar processing and out-of-order execution orthogonal? Yes. I already gave you the answer. Why or why not? Well, because multiple instruction fetch has nothing to do with in-order versus out-of-order execution of instructions. The concepts themselves are orthogonal. Assume your friend at a processor design company designed a 1 instruction-wide processor with out-of-order execution. Every instruction in this machine takes a single cycle. What would you suggest to your friend to simplify the design of the above processor? Yes?
Is there any point to having the out-of-order execution?
Exactly. So make it in order, right? That could be your suggestion. Why? Because every instruction is single cycle latency, right? There's no latency to tolerate. And we discussed this in class, right? Okay? So that's one other question from the final. I guess I'll do some of these final questions. Oh, another one. Actually, we've covered this a couple of times. Register versus memory dependencies, right? What is the fundamental difference between dependencies through registers and dependencies through memory? Explain in no more than 20 words. Again, you don't need 20 words here. Who wants to take a stab at it? Yes?
You don't know memory dependencies at the runtime?
Exactly. Yes?
Memory is accessible by other processors, but registers are for that process.
So that is answering a separate question, right? The question is about the dependencies. You're absolutely right. If the question was, what is the difference between registers and memory, that would be a right answer. But we're specifically asking about the dependencies themselves. I guess if you turn the answer a little bit such that it focused on dependencies, that could work too. But basically, what we're looking for here is register dependencies determined statically, memory dependencies determined dynamically. That's another way of answering the question. And I do not remember what the solution said, but let's see if it did a good job. Final solution. So you can actually find the solutions here too. There you go. And there's more detail. You don't need to write the more detail, by the way. Well, I guess there's, if you write this, that's enough. Register dependencies are statically known. Memory dependencies are dynamically determined. Okay? And you don't need to know about DRAM chips yet, because this was the final last year. Okay, let me go back and do one more, and then I'll leave it to Justin probably, unless you want me to do some more. But Justin's excited about solving some problems, right? Okay. Let's see, real IW superscalar array processor. Maybe we'll cover this in a little bit more detail. You should be able to answer that question also. These are coherence. You don't need to know that yet. Multiprocessing. Yeah, these we will cover when we get to things. I guess the final exam had a lot of other questions then. Okay, I guess we could do this one, right? Since you know what an array processor is. Do you know what an array processor is? Okay, let's take a stab at this one. What do VLIW, superscalar execution, and array processing concepts have in common? Remember, VLIW, multiple instructions fetched, decoded, executed a cycle, and the compiler packs those instructions together. Actually, it's a single instruction that consists of multiple operations. Right. Yes, you have an answer?
You have multiple functional units in all these processes?
Yes, but it's more than that, right? It's actually multiple operations fetched, decoded, executed in the same cycle. So that's the answer, actually. It's not only multiple functional units, but you can actually do multiple operations fetched. It's the fetch part. And decoded and executed in the same cycle. And they all do it in different ways, right? VLIW, we've already covered VLIW versus superscalar right now. But an array processor does it in a more compact way, right? A single instruction encodes multiple operations, right? On different data values. And we've covered this. But you might want to go back to your lecture notes. And that's the answer. Do you want to do more in this question, or do you want to save it for yourself? Provide 2 reasons why a VLIW microarchitecture is simpler than a same width superscalar microarchitecture. Any answer? Yes?
The superscalar microarchitecture is determining dependencies on the fly, whereas the VLIW has already had it done for it.
That's right. Exactly. That's one reason. Basically, between concurrently fetched instructions, the VLIW processor doesn't need to do anything. Because the instructions are already, the operations in that very long instruction word are independent. Compiler ensures that. Whereas superscalar processor, there's no such guarantee. You fetch 4 instructions, they all can be dependent. The hardware needs to determine those dependencies. What about another reason? This may be a tougher one. Yes?
In a VLIW machine, can it just essentially fetch one word, whereas in a superscalar it needs to have multiple pieces to fetch a bunch of different smaller pieces?
Because you have branches?
Yeah, I guess so.
But that could happen in a VLIW also, actually.
Well, it's more that you have to do with each superscalar is kind of its own little segment, which has to grab different portions. And if it's like, say, x86 or a variable length, then it will be harder to determine which piece each
instruction is?
Yeah, it's supposed to grab, whereas in VLIW it's just one little
I see.
thing you grab all at once. If that
I
makes
see.
sense.
Yeah, it's not as clear, right? Because now you're getting into variable length instructions, perhaps. With variable length instructions, with a superscalar engine, you need to determine where the next instruction is, of course. Whereas with a VLIW engine, I guess, yeah, you need to specify where the instructions are. So that might be easier.
That's the one thing the superscalar needs to specify for each where each instruction is fetching gets next, whereas in VLIW you just kind of grab the whole thing.
That's right, yes. Yeah. That's harder to explain.
Yeah.
So one of the reasons, actually, design a VLIW processor, you streamline everything such that a VLIW, very long instruction words, such that the compiler knows the structure of the machine, so that it aligns the functional unit with the instructions. So you have a multiply instruction, multiply functional unit happens here. You have an add instruction, add functional unit is here. So the machine structure is reflected in the instruction structure. So for example, the load functional unit is here, the compiler puts the load over here. The compiler doesn't put the load over here. Now what does this do? This simplifies the logic to route the instructions, right? You always fetch the load. Essentially, you have parallel pipelines, right? The load that's fetched here never goes here because the load is never placed here by the compiler in an instruction. The load is always placed in the slot 3, let's say, and you have slot 2, and you have slot 1, and then you have slot 0 in the very long instruction. Whereas with a superscalar engine, you don't have this instruction word. What happens is the load can be anywhere when it's fetched. So what you need is a way to send this load to the load functional units, and a way to send this multiply to the multiply functional unit, because it might be fetched anywhere. The compiler doesn't pack the instructions such that the movement of the instructions in the pipeline is streamlined to the functional units. Now we did not cover this in class, so you won't be expected to answer it this way. That's why this is in the final. But that's one of the other reasons. VLIW, the compiler does the work to simplify the hardware. And this is one simplification of the hardware. You don't need to, the instructions don't appear in arbitrary places that make it hard for the hardware to move them to the functional units that are far apart. Okay? Okay, let me answer the other two. Okay, provide 2 reasons why superscalar microarchitecture could provide higher performance than the same with VLIW microarchitecture. Any reasons? Remember, the compiler is packing these instructions, whereas the hardware is not packing, but it's extracting instructions here. Let's say you have 4 white VLIW. Yes?
Well, kind of going off what you're talking about with how the VLIW is broken up, and your program has a whole bunch of multiply instructions and very few load instructions, then in a VLI machine, you're still going to be pulling out a blank load all the time for each instruction, whereas in a superscalar, you're pulling out.
That's right. So yes, in that case, if the compiler cannot fit the instructions into the machine structure, it inserts more instructions. Right? Or thought another way, here the compiler needs to find 4 independent instructions, right? N independent instructions. What if the compiler cannot find N independent instructions in the cycle? It basically adds no ops. Whereas a superscalar processor doesn't have this. Right? You can always fetch the instructions and buffer them somewhere. Whereas a VLIW processor has that problem. But what you said is also true. If the compiler cannot find appropriate instructions for the slots that you have in the machine, again, you'll have bubbles. Whereas superscalar has this hardware to gracefully handle those cases where you have different instructions going into different functional units, or different slots going into different functional units. Okay. Because provide a reason why a VLIW processor is more flexible than an array processor. This could be a question that could come in your exam. We covered this. An array processor, I guess.
I was going to say a VLIW machine isn't limited to a certain combination of the same instruction repeated.
That's right, exactly. Basically, the instructions that are, the operations that are fetched and executed concurrently don't have to be the same operation. They can be totally different operations. Okay. Okay, and the last reason, provide a reason why an array processor is simpler than a same with VLIW processor. Why could the array processor be simpler than the VLIW?
The actual instructions are much simpler.
What's simpler?
The instructions are
That's right, yes. Which makes their decoding simpler, right? Basically here, in a Vliw processor, you can have, let's say, 4 different operations, which means I need to have 4 different decoders here, right? Whereas in an array processor, you exercise only 1 decoder. Let's assume that these are flexible, so this can execute, you can have any instruction here, any instruction here, any instruction here, any instruction here. It requires 4 different decoders. In an array processor, these are all the same instruction. In fact, you don't have 4 instructions in an array processor, right? You fetch 1 instruction and then distribute it to multiple data elements, which means that you just need 1 decoder. And that's the reason. Okay. You want to take over, Justin? Or any other questions? I think I'll give you 27 minutes of quality time with Justin then. And I'll sit in the back and enjoy. Okay. You don't need my computer, right?
Hi, everyone. So, yeah, so midterm coming up really soon. Office hours. So Jason has office hours tomorrow. That's good. Take advantage of those. Yungu will hopefully send out his additional office hours soon. It would probably be good if they're tomorrow afternoon, I'm guessing. Wednesday morning might be a little bit too late, right? Take advantage of those. Ask any questions that you have as you're going through these exams. Are there any like high-level administrative or just general questions that are still sort of out there for you? Or is everything in terms of the type of questions that we'll be asking and sort of the length of the exam and the difficulty, is that pretty straightforward for you guys? Okay. Okay, that's, yeah.
In the exam, like review stuff, it says since you know the stuff from the readings, will you be asking questions that are explicitly referred to them?
So I think that we have these required readings, right? So there's some papers that we've picked out that we think are particularly relevant to the topics that we're covering in class. Now, we're not going to ask you in paragraph N of this paper, what were they talking about? But if there's a concept that they spend at least a page or more talking about, or maybe there's a major diagram from that paper that we think is really important, I think that's fair game for the exam material. Yeah. So in terms of the readings, that's the kind of questions that we might pull from there. Yeah. Any other questions related to just the structure of the exam? Okay, so I think we've covered a lot of questions from the past midterm, even some from the final. We have a little bit of time, I guess. So there's a couple of questions that I think are particularly interesting, and it's important that you know the answers to from the previous midterm. So I'm just going to go through as much as we can get through before the end of the lecture. And I'm going to try and focus more on the high-level concepts that I think you should understand. For the exact answers, you can refer to the midterm itself. So I guess we can start going through those. Are there any specific questions, though, on the midterm? I guess we can start there. I had a couple predefined that I thought were interesting, but do you guys have any that you would like to hear about? Or did you get those out of your system already? Okay, cool. So one of the questions that I think it's worth reviewing is question 2. Now, when we went over when Yungu started the review, we left off on the first part of question 2. I'm going to go through more of question 2, hopefully all of it. We can talk about that. So remember, question 2 is talking about fine-grained multi-threading. Do you remember what fine-grained multi-threading is? What's special about fine-grained multi-threading? What does it let us do? Yeah.
Get rid of dependence checking.
Sorry?
Get rid of dependence checking.
You can get rid of dependence checking with fine-grained multi-threading. Why?
Because you're guaranteed that every stage of the pipeline corresponds to a different thread, so they're never going to have overlap in terms of
Yeah, so what we do with fine-grained multi-threading is we say, if I have this many stages in my pipeline, maybe, if I have n stages in my pipeline, then I'm going to have n threads, and every cycle I'm going to fetch from a different thread. And so at any point in time, there's going to be n instructions from n different threads in my pipeline. Why is this good? Because now we don't have multiple instructions from the same thread in the pipeline, so we don't have to worry about checking for dependencies between two different instructions. What's one of the downsides of fine-grained multi-threading?
It's very hard to cover along because you have to rely on your thread rate.
So, okay, so I guess let's expand on that. So could it be more difficult to program on this machine than a regular machine? I don't know. So, I mean, if it's just different programs, maybe you program all of those individual programs as if you were just running on a normal machine. You don't even know that there is this concept of threads and that each instruction is executing a different, each thread is executing a different instruction from that program. Maybe from the programmer's perspective, it's actually pretty much similar, but you can just execute multiple programs at the same time.
Yeah. Well, do you need different register files then? You don't have different.
Okay, so there you go. So now this isn't a programmer concept, but in the hardware, your hardware becomes more complex, right? Because now you have to manage the state for as many threads as you're going to have in your pipeline at the same time. Yeah, that's one thing. What's another thing with fine-grained multi-threading? Yeah?
Single thread performance goes down?
Yes. Single thread performance goes down because you're only executing one instruction from each thread every n cycles. Yeah. What if you don't have n threads on your system?
Bubbles. Bubbles.
Bubbles, exactly. So your system throughput can go down compared to same number of pipeline stages, but not fine-grained multi-threaded processor if you don't have enough processes on your system to spin up threads for. Good. OK, so that's the high level on fine-grained multi-threading. So what this question was asking, so we looked at part A. In terms of, for part B, what the question is asking is, if you just wanted to focus on branch stalls. So we're taking this system and we're dividing it into two places where there can be sort of control dependence and data dependence. So in the pipeline, there's two spots where you have dependence. One is control dependence with like branch type instructions. Another is data dependence. Control dependence happens, it enforces an ordering when you figure out the outcome to a branch. So that's at one stage in the pipeline. Data dependence, you sort of ultimately figure out when you're writing back to the register file. That's a different stage in the pipeline. So what this question is asking is, if you just focus on control dependence, how can you eliminate that aspect using fine-grained multi-threading? So what you need to do is you need to look at and see where is the outcome of the branches being predicted or being resolved, and use as many threads as you need to get up to that stage. But for data dependence, maybe you're handling that in another way, maybe with some sort of forwarding mechanism, or maybe stalling. So part B is asking, how many threads do you need if you just care about branch stalls? And the answer is really enough threads to keep all of the stages up until where you resolve branches full, right? And then and then the question is why, and that's basically the answer for why. Now the next question brings into account, what if you want to eliminate dependency check logic for dependent instructions? Now what you want to look at is, where do you actually figure out when instructions are, when an instruction can receive another instruction's dependent value, and you want to use enough threads to fill up the pipeline stages until you get to that point. So in general, what you want to do, if there's a point in your pipeline where you think you're going to stall because you need some other information, and you don't want to stall with fine-grained multi-threading, just fill in independent threads in all of the stages before that point in the pipeline. That's the general approach to solving these type of questions. Okay? So that's B and C. Now, if we look at D, basically what D is talking about is if we were to change the assumptions about how many stages there are for fetch, decode, execute, if we were to change the assumptions about when branches are resolved, about when data dependencies are resolved, how does that change the number of threads that you need in the system? Well, the high-level sketch is just like before, right? We just look at this new pipeline, and we figure out where are the points where these dependencies exist, and how many threads do we need to fill up the pipeline up until that point. It's the same strategy. We're just applying it to a different machine in this part of the question. Right? Now, and you can, like I said, I'm trying to give you just the high-level sketch so you can understand if you see a similar problem on the upcoming exam, you'll be able to apply this technique to those type of problems, right? So the next part of the question, E, is asking, it's a performance question, and it's asking what's the minimum number of cycles per instruction? If cycles per instruction is low, what does that mean? Is that good or bad? Do we want low cycles per instruction or high cycles per instruction? We want low cycles per instruction. Each instruction takes a short amount of time to execute. So we say, if you use a certain number of threads on one machine, what are the minimum number of cycles per instruction for each thread? Right? So how would you go about figuring that out? If we said, here's a pipeline. Here's the number of threads that we're using. What's the minimum number of cycles that we need to execute each thread? Any thoughts? Yeah?
By the constraints we've imposed, there's only one instruction from the thread at any given time in the pipeline. So you can just draft whatever that comes into the fetch stage until whenever that leaves from the write back stage. And that's the number of instructions that it's going to take to process, or number of cycles it's going to take to process that one instruction in the thread.
Yeah, exactly. So we've given you the pipeline. And at most, we have one instruction from each thread in the pipeline at a time. And the number of cycles it takes to execute that one instruction is equal to the number of pipeline stages that that instruction goes through. So for example, if we have a certain instruction that is fetched, is decoded, is executed, is written back, it goes through all of the stages in the pipeline. So the cycles per each instruction like that is just is equal to the number of stages in your pipeline. What if you just have branch instructions? Well, then maybe it's not the full length of the pipeline, because branch instructions don't need to write back some sort of data to the register file, right? Then the number of cycles per instruction, if you only have branches in your code, is the number of stages it takes to get to the point where you've resolved the branch. And then you grab a new branch, and then it's the same number of pipeline stages for that branch, same number of cycles. Then you grab another branch, okay? And that's what this question is asking, is if you're just looking at instructions that are branches, what is the maximum performance that you could achieve? It's just the number of pipeline stages with each cycle moving an instruction through another pipeline stage that it takes to get to that point where you resolve the branch. Okay, so any questions so far? Yeah.
I was going to say, so as far as the branch goes, though, wouldn't it still be true that another instruction from that same thread wouldn't be able to enter the pipeline until after the branch has gone through the write back, even though write back hasn't even put anything to the branch? Would that still be true?
Say that again?
So if you have the case where your branch instruction from one of your threads goes all the way through, when it's in the write back stage, won't the last thread in the ordering be in the fetch stage? Is that correct? So if you have a 5-stage pipeline and you have thread 1 in the write back stage, even if that instruction was a branch, wouldn't you have thread 5 in the fetch stage at that point?
Yes, yes.
Okay.
Yeah.
So you would still have to wait for the additional cycle in order to have thread 1's instruction fully complete.
I mean, yeah, you would have to wait. I mean, if each stage takes 1 cycle to execute, you would have to wait for that last stage to finish. To finish its operations. But what was, I don't think I understood the question.
I guess I was kind of confused when you were saying that the instruction is effectively done whenever the branch is resolved, even though the branch is still in the pipeline.
Okay, yeah. So,
I mean, it's not everything useful that's going to do,
yeah,
but it's still there.
So it's still, so the thing is though, the branch is going to change where you start fetching instructions from, right? So you're going to start fetching instructions from a different point in the program. Right. So you can think of when you finish a branch, it's basically done. Like, do you count that as part of the number of cycles that it takes to execute that instruction while it's waiting in the pipeline to go to the retire stage? Not necessarily, because you're still making forward progress. You're still doing work and you're still fetching new instructions, right? You need to take that into account. Yeah. There's actually, on that question, on that note specifically, there's another question in the midterm that I think it would be really useful for you to go over, which is, I think it's question 6. Data dependence handling. Take a look and make sure you understand parts A and B to question 6. That's really important for measuring performance in the processor. So make sure you understand those parts. I thought I saw a hand over here.
I was just going to say that like that specific part of the question isn't like worrying about other types of data dependencies, right?
Yeah, exactly. So we're
it's just looking for just like if all of your instructions were branches,
yes,
the minimum time you would need for all of those branches to like work correctly.
Right.
You would only need like until the branch is evaluated. You wouldn't need the whole pipeline.
Yeah, exactly. So we specified in that question, assume that everything is just branches, right? And what's the minimum amount of time you would need to satisfy those branches? Well, it's until you resolve their target destination. And then the next question is just, now it's looking at data dependencies, and how many stages would that require? Well, we altered the assumptions of the pipeline now, so you need to go back and see where our data dependencies resolved. And that will tell you the number of threads that you need to keep the pipeline full of independent instructions from different threads. So it's the same concept over and over again, but we're just we're changing some of the assumptions and asking you to sort of use those new assumptions to reason about what might happen in the system. Same thing, we ask you for performance now with the data dependencies. Hopefully you can answer that. You just need to look at how long does it take to complete these instructions? Well, now they're going through the full pipeline, so it's going to take more cycles per instruction than if you were just looking at control dependence instructions. And you'll see that in the answer. So why might a fine-grained multi-threaded machine like the one we've been discussing actually run slower than if you just use a pipeline machine? Let's say you have enough threads even to fill up all of the stages. Yeah?
You have to like pick and choose between the right thread, and you have to like you have to remember like which thread is which, and determine what the next thread is and everything like that.
Yeah, so what Andrew's getting at is we have to keep track of a lot of information now, right? We have to keep track of which thread is going to execute next. That takes some logic to select the next thread. Even if it's a really simple method for selecting the next thread, like round robin, that's still some logic. That's still increasing potentially our critical path through one of the stages, like the fetch stage. We might require larger structures to hold all of the data associated with these threads. Those larger structures might take a longer time to access than if we just had smaller structures with a normal pipeline machine. It's another thing to consider. Yeah. So basically, the additional hardware cost could actually affect performance as well. Okay. Question 3 on branch prediction. So I think we've gone over some branch prediction. I think the high-level overview that Professor Mutlu gave is good. Be familiar with those different types of branch predictors. Do some examples. Maybe take this branch prediction problem and figure out, for the different types of predictors that we talked about, what would the prediction accuracy be for the branches that are in this problem? I think that's a really good exercise to perform. So that was one of the questions that I wanted to sort of highlight. I was looking over the questions that were, we talked about what was the distribution of how questions were, what were the score distributions per question. And I noticed that the 2 lowest ones, it seems like 2 that people kind of skipped because most people actually got between 0 and 10 points on this question, was what does this mystery instruction do? That's question 4. And also the one that we talked about but didn't answer yet, which was what does this logic do? 7. So it's kind of like the what does this blank do questions. And I don't know exactly, but I think people looked at these questions and thought, the first one looks really long and complicated. I'm going to save that for later, and maybe they ran out of time. The later one, maybe they got to that one later on, said, I don't really know what's going on, and skipped it. So I think in the case of what does this mystery instruction do, I think it is time consuming, but I think it's relatively reasonable to work through. You just need to do the same things that you've been doing, that you did, hopefully, for the microcoded homework assignment, which is figure out the control signals that are being asserted and use your understanding of the machine, which we provide all the diagrams for, to figure out what is actually going on systematically. That one, I think, is time-consuming but relatively straightforward. I think the time-consuming part is why people skipped it. Question 7, what does this logic do? I think that one's actually more challenging, even though it's maybe less time-consuming if you see it right away. So I think maybe a lot of people skipped that just because it was very difficult to reason about what was going on. But if you understand how register renaming works in a machine, I think that one is also relatively reasonable to try and walk through and understand. Okay? So I bring this up because I just wanted to get back to that question we had about what were the questions that people tended to get the lowest scores on. It happened to be those 2. And I think they're both challenging but doable. OK, so we have about 4 minutes. Now, when we had a little bit of downtime during Friday's lecture, I talked a bit about Tomasulo's algorithm. Be very familiar with Tomasulo's algorithm. I think that's a very important algorithm to know. And also, I guess the other side of it is it's an algorithm. So once you know the steps, the straightforward steps for how it operates, you can apply it to different situations. So take a look at question 5. This is on out-of-order execution. This is typical of the kind of question that we might ask you on the exam, which is we give you some sort of state of a machine, like I was talking about on Friday, and we ask you to figure out maybe what were the instructions that led to this state. I'm going to sketch the high-level way that I would go about solving this problem, and I think you could apply this to other variants of this technique. So in general, what you're going to want to do is you're going to want to look at the register alias table, which, remember, maps register names to their values and whether they're valid or not. And we give you the reservation stations for each of the execution units. What you're first going to want to do is look at, in the reservation stations, what has been reserved, what are the operands, and where are they writing to. That basically gives you all of the instructions that are currently in the machine waiting to be executed. Those are kind of like freebie instructions that you know for sure have already been fetched and are ready to execute. And you can pretty much fill in what the registers are by looking back at the register alias table. So you can see in the reservation station, it's waiting for B, or it's waiting for A here. A has been tagged for register 2, okay, one of its operands is register 2 for this multiply. It's writing into Z, so the destination is register 6. You can do this for all of the reservation station entries that are occupied. For instructions that already executed that you don't see in the machine, even those you can infer to some extent. You can take a look at the contents of the register file and see, okay, well, one of the entries in the register file has been tagged by an instruction that's no longer in the reservation stations, and it's valid. That means it already executed. To figure out what its operands were, you could look into the register alias table and see what are the potential operations on the data values that are in the register alias table that could have led to the value that's stored in this register. Right? Does that make sense? You can look at a register, see how it's tagged, and then look at what its resulting value was to figure out what were the other registers that could have been combined, let's say multiplied together, to get that value. That gives you, that sort of unlocks other instructions that you can now reason about. When you know the instructions and have figured out the tags for their destinations and sources, now you can start to order them in relation to one another. If one of the instructions reads data from a register that's tagged A, and another instruction writes data to a register that's tagged A, well, the one that wrote data to the register tagged A had to have come before the one that reads data from the register tagged A. So now you can start to impose this order. So step 1, look at the state of the machine, look at the reservation stations, figure out the in-flight instructions. Step 2, look at the register alias table, figure out what instructions could have executed, and what would their source and destination registers have been. Step 3, order the instructions with respect to one another using their renamed values for the registers. And then from that point, you'll get the program order. You can draw a data flow graph if you want from that point. You can draw the per cycle execution of it. You can even figure out at any given cycle what was the equivalent state of the machine. Familiarize yourself with this approach to solving the questions. There's additional Tomasulo questions on the other exams. OK, I'm out of time. If you have questions, go to the TA's office hours. Good luck studying. I hope you all do really well on the exam.